Okay, for this next chapter, what we need to learn more about is SN2 reactions. And we're going to combine the different topics of stereochemistry together with the concept of SN2 and then SN1 reactions to understand how substitution affects the stereochemistry. The first thing we want to start off with is the SN2 reaction of R2-bromobutane with sodium chloride. And there's a couple of interesting things about this reaction. In the past, when we saw SN2 reactions, the first thing that we had to do was protonate the alcohol to turn the water into a leaving group, and then we used usually a bromide ion to come along and push that water off as a leaving group. And that's what we saw with the SN2 reactions when you have an alcohol. When we have an alkyl halide, like this 2-bromobutane, and it has this halogen right there, you don't need to pre-protonate the halogen in order to get it to fall off. And that's because bromine is a good leaving group. That's a new term. I think I've thrown that around before, but we need to define that term more precisely. A leaving group is an atom or group of atoms, so it is a portion of the molecule that leaves, and that seems pretty obvious. And a good leaving group disrupts the solvent as little as possible. So the way to think about this is when this bromide ion right here gets pushed off. And so a chloride ion is going to come along and push off the bromide ion. And we can ignore the rest of the details for a second and just focus on the overall chemistry. Chloride hits the carbon electrophile, knocks off the bromide as a leaving group, and we end up with 2-chlorobutane as our product. In this case, the bromide is the leaving group, and when that bromide is pushed off into the solvent has to package and wrap itself around that negative charge. The more solvent molecules that it takes in order to stabilize that negative charge, and kind of the more insult that occurs to each of those solvent molecules, the more problematic this is going to be in terms of energy. And the reason that it's an insult is that the negative charge of the bromide ion typically is not very soluble inside of an organic solvent. And so a good leaving group is one that the solvent can more easily solvate. So the reactivity of leaving groups, a good leaving group disrupts the solvent as little as possible. And typically, a good leaving group has a large diffuse charge, negative charge. Okay, so that's a lot in that definition, and we're going to come and look at some more examples of that. But this is the key concept. A good leaving group has a large diffuse negative charge. So now let's think about this mechanism again. Chloride is a smaller ion than the bromide ion is. So during the course of the chemical reaction, the chloride ion acts as a nucleophile. Remember, a nucleophile is a Lewis base. A Lewis base is an electron pair donor. The chloride ion pushes its electrons into the carbon and bumps off the bromide ion. From the solvent's perspective, assuming that this is a typical non-polar organic solvent, this is a win. The chloride ion is a smaller, more compact ion. The negative charge is concentrated as a -1 charge over a smaller area. The bromide ion is a larger, more diffuse ion. And one of the ways to think about this is imagine something that weighs 2,000 pounds. And you and a group of friends decide to lift that 2,000-pound object. If that 2,000-pound object is the size of a car, then you can spread people around the car and collectively pick up and move a 2,000-pound car. That's kind of what the bromide ion is like. It's this large negative charge. Chloride has the same negative charge. So in this analogy, the chloride still weighs 2,000 pounds, only it's much smaller. So now you're looking at trying to pick up, let's say, a tennis ball that weighs 2,000 pounds. And while they have the same mass, you just have a harder time getting everybody's hands in position to lift up that 2,000-pound tennis ball. And that's how the solvent feels about the chloride ion. From the solvent's perspective, it's more difficult to solvate, that's the word, to solvate a chloride ion than it is a bromide ion. So energetically, trading the chloride ion in the solvent for a bromide ion is energetically downhill. Bromide is a better leaving group because the negative charge is distributed over a larger ion. Of the halogens then, hopefully you can guess of the 4 common halogens which one is the best leaving group and which one is the worst leaving group. Iodide is the best leaving group because all of them would have a negative charge. The iodide just tends to be very large. Fluoride is the worst leaving group, and it has the same -1 charge. It's just a very small compact ion. It would be like a 2,000-pound marble. So very difficult for the solvent to stabilize a fluoride ion in solution. Okay, so now let's think again about the energetics of this reaction. We started off with we start off with an ion and a molecule that were at some inherent energy level. And because the bromide ion insults the solvent less and is a better leaving group than the chloride ion, then we expect this reaction to go energetically downhill. It still has this transition state, and the transition state is worth thinking about. Every time you encounter a hump in your energy diagram, that's going to be represented by a transition state. Overall, this reaction is exothermic, and so this will have an early transition state. It's not that exothermic, so it's not that early. But by Hammond's postulate, an exothermic reaction has an early transition state. During the transition state, there is this moment where the carbon has essentially half of a bond to a bromine as the bromine is leaving, and half of a bond to a chlorine as the chloride is coming in. So in terms of electron groups, this carbon essentially has 5 electron groups. And while 5 electron groups is not an electron geometry that I asked you to learn earlier, you need to know it, and it's trigonal bipyramidal, or trigonal bipyramidal. I'm not sure which way you're supposed to pronounce that. The key, though, is that across the center of this compound, the hydrogen, the methyl group, and the ethyl group are going to flatten out. And so as the chloride starts to, as you think about crawling up this energy diagram right here, as the chloride is pushing its electron density in as a nucleophile, and the bromide is leaving as a leaving group, then these 3 groups, the hydrogen, the ethyl, and the methyl, flatten out, kind of like an umbrella that starts to invert. And that's exactly what happens when the bromide, as we roll down the slope here, and that bromide departs entirely, that chloride formalizes the bond, the bromide is leaving, and that opens up a hole of electron density. As the bromide leaves, there's no electron density here, so the hydrogen, the ethyl group, and the methyl group slide over and fill that hole. And what we ended up doing was fully inverting the umbrella. This is characteristic specifically of SN2 reactions. During the course of an SN2 reaction, you will typically invert the stereochemistry of the various atoms that surround the carbon. And you'll notice that here in the name. This started off as R2-bromobutane, and it ended as S2-chlorobutane. This stereochemical inversion is a common feature. In fact, it's one of the defining features of an SN2 chemical reaction. So stereochemical inversion is a defining feature of SN2 reactions. I spent quite a bit of time in graduate school trying to build a chiral center specifically so that we could monitor whether or not the stereochemistry flipped or not during the course of a chemical reaction, so that we could determine if the enzyme was catalyzing an SN2 or an SN1 reaction. So stereochemical inversion is the defining feature of SN2 reactions where the chiral carbon, and because it could be other atoms besides carbon, but it's usually carbon, the chiral center, usually a carbon, is flipped from R to S or S to R. It depends on what it started out as. If it started off as S, then we expect it to flip to R. If it starts off as R, then it flips over to S. So this is the concept of stereochemical inversion. Okay, so let's see what we've done here with this question. Show an energy diagram for the SN2 reaction of R2-bromobutane with sodium chloride. This just has one step. A chemical reaction that has a single mechanistic step is referred to as concerted. And so this particular, the mechanism is concerted, and that means that it has one step, and we only see one transition state. I was over 2 on spelling that thing. It's transition. There we go. Okay, that's a term that shows up quite a bit, and it's a useful term to remember. Let's kind of look now at why I have some other pictures drawn around here. So I have here the transition state that I showed specifically. So it says draw the structure of the transition state. And here's my transition state. It is the shape of the molecule at that halfway point. And this transition state has trigonal bipyramidal geometry. And the flattening out of the center 3 groups coming off that carbon are what lead to that inversion of the stereocenter. Specify the stereochemistry of the product, so I went from R to S. And again, that's a common feature of these SN2 type reactions. Now you might ask, how was I supposed to know that this reaction was going to undergo an SN2 reaction? And what happens if it does SN1? If the bromide falls off and you end up with a carbocation and then the chloride comes in? Well, that's a good question. And it's a question we'll answer later on. We'll come up with another table similar to the DUI table that allows you to look at your starting material and predict what the mechanism will be. For now, it's SN2 because the question tells you it's SN2. These last diagrams right here show kind of the progression of the orbital. So the bond between this carbon right here and that bromine, that's an sp3 hybridized carbon. 4 different groups coming off of it. This is the typical shape of an sp3 hybridized carbon. The chloride pushes its electron density into this backside nodule. And in fact, this nucleophilic attack in an SN2 reaction is called backside attack. That's the common term that we say without laughing as organic chemists, that it's a backside attack. Every time I tell people that I teach chemical reactions and we discuss backside attacks, they always snicker. And so don't. It's just the terminology we use. During that backside attack, the electron density starts to fill in this nodule, and at the transition state, the carbon really doesn't know which of those 2 portions of the orbital are actually the ones involved in the bonding. You are at the halfway point, and so this side of the orbital has exactly the same amount of electron density as this side of the orbital, and it's essentially at this point like an overfilled p orbital. And so when the bromide leaves, then we end up with that same sp3 looking orbital, but we've switched. The side that used to be the non-bonding portion of that orbital that we would ignore in all of our diagrams has now become the bonding portion of our orbital, and the bonding portion of the orbital has kind of has shrunk until it's the non-bonding portion of the orbital. This particular diagram, it's not part of the question, but this is what I see in my mind when I look at an SN2 reaction, that the chloride is specifically targeting its electron density at this little backside nodule, and that's why the reaction has to occur 180 degrees or directly across the carbon atom from the leaving group. And this backside attack is going to dictate the reactivity of some of these compounds in later questions. So you need to recognize that every time this nucleophilic attack occurs, it actually has to line up at 180 degrees. And that's part of the reason that SN2 reactions tend to be fairly slow, is you not only need the atoms to come together, in this case the chloride ion has to come together with the 2-bromobutane, in the right orientation and the right energy. That's a lot to ask for. If the chloride bumps into this carbon atom but not directly behind it, then no chemical reaction can occur. It has to specifically hit this little teeny target. And I kind of see that as the episode 4 of Star Wars, where Luke Skywalker guides the photon torpedo into the one little hole in the ventilation system of the Death Star, or whatever it is. And at this point, I don't know Star Wars well enough to continue the analogy. But that's what I picture when I see an SN2 reaction. Okay, we've addressed all of the questions that we want to look at with this, and now we're ready to move on to the next question. For this one right here, we want to look at some more SN2 reactions. And the reason that they're SN2 now starts to become important. Generally speaking, alkyl halides, such as 2-bromobutane, 2-chlorobutane, 2-isobutane, that we built in the last chapter, have a tendency to react via SN2. And there's sometimes they're going to react via SN1, and we'll deal with those another day. For today, these secondary alkyl halides, and here's the Fischer projection of the first one, the 2-bromobutane. It's secondary because the halogen is directly connected to a carbon. That carbon is bound to 2 other carbons, so this is a secondary alkyl halide. A secondary alkyl halide has a tendency to react in a substitution that is SN2. There's some times that it doesn't, and we'll deal with those later. This nucleophile is now different than my previous nucleophile. In the previous reaction, I used a chloride ion as a nucleophile. This is called a thiolate. So this particular nucleophile, the thiolate, it is a good nucleophile. And the reason that something is a good nucleophile is it needs to do 2 things. Okay? So nucleophilicity is what we want to define next. It is the ability of a compound, and so it could be a molecule or an ion or even a single atom or ion, although it's usually an ion. So most of the time the nucleophiles that we encounter are actually ions, and that has to do, and that's because that's what the nucleophile needs to do, is it needs to throw electrons. So if you're an anion, then you're going to be able to throw electrons better. So it's actually most of the time nucleophiles are anions. We should be more specific because cations with positive charges are really bad nucleophiles. So again, ability of a compound to 1, summon extra electron density, and 2, throw or donate that electron density toward an electrophile. Ability of, I'll change that right there. So it's ability of a compound to summon electron density and donate that extra electron density towards an electrophile. So for the chloride ion, it can summon its electron density pretty well. It's because it has a net negative charge. It's easier for anions to do that. So part 1 is done. The second part of the definition of a nucleophile is that it has to donate its electron density towards the electrophile. And that's what that arrow is showing there. And now you ask, well, how well does chloride do that? And the answer is not super well. Chlorine is an unusually electronegative atom. It's number 3 on the list of all-time greatest electronegative hits. So the chloride ion is actually not very good at tossing its electrons at something. And so because it has a negative charge, it's still considered to be a pretty good electrophile, but compared to bromide and this thiolate, the chloride actually has the same -1 charge. So chloride, bromide, and the thiolate all have a -1 charge, but this sulfur here is less electronegative than the chlorine, which means that it's easier for the sulfur to throw its electron density into that carbon. So that's what makes something a good nucleophile. The ability to have extra electrons, usually a negative charge, and then the ability to throw those by not being very electronegative. So we'll make a note here. The ability to donate the electron density toward an electrophile, and so generally lower electronegativity is equal to stronger nucleophile. Capital E, capital N is kind of a standard abbreviation for electronegativity or electronegative. Okay, so what is this question actually getting at? Well, the nucleophile in all 3 of these reactions is the same. And you might ask yourself, well, what happened to the lithium? And the short answer is absolutely nobody cares. Lithium is a spectator ion and is therefore the middle child of chemistry, the thing that nobody cares about. So this sulfide ion right here, as it throws itself into that carbon, you have to think about the variables here. And when we ask, so we're supposed to rank these in terms of fastest to slowest. Well, in all 3 examples that I've shown you, it's that same sulfur. So being a strong or a weak nucleophile is not actually the difference that we need to focus on in this particular question. The other difference that we don't have to worry about is, and we're going to see this in the next question, is what happens when I start changing around the carbons. But for these compounds, in all cases, the carbons have essentially the same environment. What I've changed is the leaving group. In question A, the bromide is a leaving group. In question B, it's a chloride as a leaving group. And in question C, it's an iodide as a leaving group. So the difference between these three is only a difference of the leaving groups. And the fastest reaction will be the one with the best leaving group. And as I explained before, a good leaving group, let's go back up and reread our definition. Leaving group is a portion of the molecule that leaves. So in the reaction that we're looking at, it's either a bromide, a chloride, or an iodide. A good leaving group disrupts the solvent as little as possible. Typically, a good leaving group has a large diffuse negative charge. And so here, when the iodide falls off versus a chloride falling off versus a bromide falling off, the iodide is the largest, most diffuse negative charge. And so a maximum number of solvent molecules can wrap themselves around the iodide, and this spreads out kind of the pain of dealing with the iodide. So you have 2,000-pound weight, but you've spread that out over a very, very large area, and you can pack a bunch of solvent molecules in there to pick that weight up. So this last compound, so A, we'll get back into in a second, and then B, but now we're looking at C. This is example C. This is the bottom one right here with the iodide, and this is the fastest reaction because it has the best leaving group. And good versus bad leaving groups, best versus worst, that's all based on rate. So the iodide falls off very quickly. This is a concerted reaction. It just has one step, so that one step is the rate determining step. And in that rate determining step, this iodide falls off very easily. That drives the reaction faster, and that's what makes it a better leaving group. Of the remaining two right here, the chloride is the worst leaving group of all three of them. It is the smallest negative charge. It's not distributed across the very large ion, and so this would be the slowest reaction because it has the worst leaving group. For the sake of your own notes, you should say, we'll add this in the bottom, and in terms of the halogens, actually they're halide leaving groups. Iodine is faster than bromine, is faster than chlorine, and is much, much, much faster than fluorine. And so fluorine, just so you know what that greater than less than symbol is referring to, fluorine is the slowest. So somewhere in your notes, you want to make sure that you have that written down so that when you forget about it on the exam and you're licking your wounds, you can go back and feel really bad because you actually wrote it down and forgot to learn it. Finally, the first one right here, the bromine's kind of the middle ground. And so this is the middleist. I have no idea what you look, the middleist. That sounds like that's the wrong word. Reaction, because it has the middleist leaving group. Just making up words right and left right here. Because it has. All right, so question number 2, the whole point of this question, the reason that you want to do this, is so that you can identify the rate of a reaction based on the suitability of the leaving groups. And the only leaving groups that we focused on so far are the halogens, and the bigger halogens are faster leaving groups. Okay, what bonus learning can we get out of this question? Well, it's a good opportunity for you to practice your your Fisher projections. But if you're just rewriting down everything I said and you skip to that practice, then is there anything else you can learn from this question? And the answer is yes. Notice how in this nucleophilic attack, that's an SN2 reaction, we expect to see inversion of the stereocenter. And in a Fisher projection, if you want to invert the stereocenter, you just flip them horizontally. So during an SN2 reaction, if you're trying to model that with Fisher projections, you need to switch the nucleophile off to the opposite side of the leaving group right here. This hydrogen does indeed get pushed over to the other side when the sulfide comes in here and hits that thing. All right, next question. Show a mechanism for the following reactions, and again, we're going to rank them from fastest to slowest and explain why the reactions occur at different rates. So there's three general variables that we want to focus on. The first variable that we looked at was the suitability of the leaving group. Well, in this particular example, all three leaving groups are the same. In every case, I'm pushing off a bromide. So I've got the three mechanisms shown here. Let's just focus on the first one for now. I'm going to use that same thiolate. And again, lithium doesn't show up in my mechanism because it's a spectator ion and nobody cares. So this sulfur with a negative charge can be called either a thiolate or a sulfide. I'll use sulfide because I'm more certain that that's the correct name for this thing. The sulfide will come over here and smack the carbon directly in the back. Okay? I always envision slapping somebody that wears glasses in the back of the head to try to get their glasses to fall off. Because, yes, I've done that to my brother and other people. So they didn't appreciate it. The sulfide will come along and smack that carbon in the back. It pushes the bromide off. This is a concerted mechanism. There is only one step. That rate-determining step involves these two things coming together. That's why it's SN2. And in fact, the energy diagram for all of these reactions that we've looked at so far will look exactly like this. You start off at a higher energy spot than you end, and you go over some type of activation barrier. Stereochemistry gets inverted in these reactions, but since this is not a chiral center, I didn't bother to show that. There's no stereochemistry here to worry about. The only difference between each of these different compounds, it's not the bromide leaving group, it's not the sulfide nucleophile, it has to do with the carbons. And so here are all the mechanisms, and hopefully you'll see the similarities. The sulfide pushes into the carbon and bumps off the bromide. This is the nucleophile, this is a backside attack, that's your leaving group. The sulfide pushes into the carbon and bumps off the leaving group. The sulfide pushes into the carbon and bumps off the leaving group. Same mechanism, same nucleophile, same leaving group in all three cases. So the only variable that we're looking at, is the electrophilic carbon. And so what we find is in terms of the rate of the reaction, the fastest to slowest. Let me make sure that, so I'm kind of setting this up as a key so that when I write the greater than less than sign, you can understand what I'm saying. We find that methyl is faster than primary alkyl halides, and that's faster than secondary alkyl halides, which is, well, tertiary alkyl halides don't undergo an SN2 reaction. So in terms of the rate of the SN2 reaction, we'll see later on that SN1 is what applies to tertiary alkyl halides, and so we're not going to put in tertiary yet. So now we're ready to address the question. In terms of the rate of the reaction of an SN2 reaction, which is all we're focusing on so far in this worksheet, this is a methyl bromide, and so that's methyl. This would be the fastest. The second one over here is an ethyl bromide. So if we look at the bromine, it's connected to a carbon. The carbon is only connected to one other carbon, so that's a primary alkyl halide. Primary alkyl halides are slower than methyl alkyl halides. And the third one here is, we jumped all the way to tertiary. So I guess I have to put that in there. This actually is much, much, much slower when we have tertiary alkyl halides. And hopefully you kind of are starting to figure out why that is, but I will definitely say it explicitly here in a second. In fact, it's so slow to do an SN2 reaction with tertiary alkyl halides that it actually is better to do SN1, which we're not going to learn about until tomorrow or whenever you watch the video. So this right here tells us that this first one, we can say this now, that A is the fastest and C is the slowest. And therefore B is not the fastest or the slowest, it's the middlest. And to avoid using ridiculous words, I'll just identify A as faster than C. And you'll kind of assume B there. Okay. I can't not do that. So A is faster than B, is much, much, much faster than C. Explain why these reactions. Okay, so now why? Why is it that it's easier for the sulfide to hit this carbon than it is for the sulfide to hit that carbon, and it's almost impossible for this sulfide to come in here and slap that carbon in the back of the head? And the answer is sterics. So this is one of the vocab terms, steric effects. And during an SN2 reaction, which is a backside attack, the more substituted carbon is sterically hindered and reacts slower. So what does that mean? Well, imagine that you're this sulfide right here and you're trying to drop your electrons into that carbon's backside there. That's going to be difficult because you have some things in your way. Well, these hydrogens are actually pretty small, so they don't really get in your way, so this won't be hard. Whereas this sulfide is going to have to work its way around that methyl group. And that methyl group has its own 3 hydrogens. They're kind of whirring around like helicopter blades, and that makes it very difficult for that thing to fit in relative to if it's just 3 hydrogens. And now when you have 3 spinning helicopter blades, it just gets chopped up on the way in, and it doesn't tend to react in the way that we're showing here as SN2. So this is just a low probability event because there's just so many things that are obstructing that sulfide ion from actually being able to put its electrons into that backside position in order to cause the chemistry to occur. Okay, so hopefully now you appreciate the variables that are important. So far we have looked first at, in the question number 2, we focused on leaving groups, and we came up with some rules for which leaving group is the fastest and which leaving group is the slowest. In question number 3, we looked at steric hindrance of the carbon, and so it tells me to explain why the reaction occurs at different rates. And so the more sterically hindered carbon is slower. And in this case, the tertiary is more sterically hindered than the primary is more sterically hindered than the methyl group. And that's the general trend. And hopefully you can see that the secondary would kind of slide here in the middle if I had chosen an example with a secondary carbon electrophile. All right, now we're ready for the third variable. And what happens if we change the nucleophile? So now I have the same leaving group, a bromide, the same carbon, an ethyl group, or in this case, a primary alkyl halide. All 3 of these are primary alkyl halides. And now what I'm doing is changing the nucleophile. So we have an iodide versus a chloride versus water, which is quite a bit different. And so the mechanism for all of these reactions, which the question doesn't specifically ask for, but you really need to think about what's going on mechanistically. In all cases, it's still that SN2 reaction. The iodide is tossing its electrons at the backside of the carbon, slaps it in the back of the head, the bromide falls off, we invert the carbon, but it's not a stereocenter, so nobody notices because there's no R or S labels, and we end up with our final product. It's concerted, one step. And in that one step, both of these are involved, so this is a classic SN2 reaction. The iodide is the nucleophile here. I just copied and pasted the same mechanism right here, and I just changed out an iodide for a chloride. Let's now go back and revisit what it is that makes something a good nucleophile. So nucleophilicity is the ability of a compound to, 1, summon extra electron density, and then 2, donate that electron density toward an electrophile. So both of these nucleophiles, the first 2, the iodide and the chloride, both have a negative charge. So in terms of the first criteria of being a nucleophile, they have the same amount of extra electron density. So the only difference is that second criteria. Which of one of these is better at throwing that electron density at some external target, and that's a function of electronegativity. Chloride, and then I wanted to change it to chlorine mid-sentence. So chlorine is evidently how that comes out. So this chlorine right here is more electronegative than an iodine, which means that the chloride ion pulls its electrons in tighter, and that makes it harder for the chloride to throw its electrons at that carbon. Chloride's still a pretty good nucleophile because it has that -1 charge, but compared to iodide, it's actually a weaker nucleophile. And even though nucleophiles and leaving groups tend to be paired up as, you think about them as opposites, they're not really opposites. So it's perfectly fine that iodide is both a better leaving group because the solvent doesn't care as much, and also a better nucleophile because it can throw its electrons in more easily. I think about iodide as kind of easy on, easy off. It's a great nucleophile, and it's also a great leaving group. So in terms of the reaction of these two right here, this will definitely go faster, much faster, because in the rate determining step, it's a better nucleophile and reacts more quickly. Now let's think about water. This is kind of a very different reaction at first glance, but when we dig into it, hopefully you can appreciate that it's pretty similar. First step is still the same. This is an SN2 reaction. The water reacts as a nucleophile and pushes into that carbon and bounces off the bromide. So I did just copy and paste this same diagram down here, and then I just changed out the chloride ion for a water molecule. Problem is, when you bring water in as a nucleophile, it has an extra proton, so that bromide leaving group actually needs to pull the hydrogen off. And I'll show you later on that you can either use the bromide to do this, or you could use another water molecule. It kind of depends on how much water is floating along in your solvent. And it's usually really hard not to have. If you're committed to putting water inside of your chemical reaction, then water tends to be everywhere and do everything. So it's better actually to show water, and I'll use that in the next one, but I wanted to give you one example where you can actually use that halide leaving group as a conjugate base and rip that hydrogen off in the next step. So is it still SN2? Well, yeah, like we definitely substituted things. We substituted a bromide for an alcohol, and the rate determining step, well, even if you don't know which of the two is the rate determining step, both steps involve two separate things coming together. So the rate determining step, though, is not the acid-base chemistry step. This first step is the rate determining step. It involves these two things coming together with a nucleophile attacking it. So this is standard SN2. It just kind of has this little piece at the end where we have to do some acid-base chemistry. And that's pretty common with alcohols. So now, of the three, we've got the three mechanisms here. And this one is still SN2. It just has this little extra step on the end. We ask which one of these is the fastest. Well, if you're thinking acid-base chemistry is super fast, so this one down here with the acid-base chemistry step is the fastest, then you're absolutely wrong. The speed of a chemical reaction only depends on the rate determining step. So the acid-base chemistry doesn't happen until we get past the rate determining step. So we still are asking about this. This is the rate determining step. It's the nucleophile coming in. And of the two criteria, water does not have a negative charge. So it doesn't have as much negative charge to throw around, and it's more electronegative than the chloride ion. So it's going to throw those electrons in more slowly. So it's actually kind of loses in terms of both of the criteria. So of these three, the iodide is the fastest, the chloride is the second fastest, and the water is the third fastest. But the water is actually not as far behind the chloride as you might expect. The chloride ion is larger, and so sometimes it moves a little more slowly. Water is incredibly small. It's a very, very small molecule. There tends to be a lot of it present in solutions. So water is still, even though it's neutrally charged, and even though the oxygen is very electronegative, it's still a pretty impressive nucleophile. So, but it's a close third place. So we would say that iodide is faster than chloride, is faster than water. And we should probably put barely. Chloride is actually barely faster than the water. You never want to underestimate the sneakiness of water. And so that's kind of the explanation. Did it ask for explain why the reactions occur at different rates? But we do need to have a clear ranking system. So the iodide is letter A, letter B is the chloride, and letter C is the water. So A is faster than B, is barely faster than C. Now, perhaps you noticed that this reaction right here is the exact reverse of the DUI table, meaning that notice that there's two products of this reaction. One is an alcohol that happens to be a primary alcohol, and the other is hydrobromic acid. So as this reaction is occurring inside of a reaction flask, you're starting to build up alcohol and you're building up hydrobromic acid. And so when you mix a primary alcohol together with hydrobromic acid, we saw from the DUI table that they react in an SN2 fashion. Primary alcohols react with hydrobromic acid in an SN2 fashion. And the reverse reaction of the alcohol reacting with hydrobromic acid, in the first step, the alcohol would get protonated, and we get this exact same middle intermediate, and then the water would be replaced by the bromide. Instead of the bromide coming in and ripping a hydrogen off, the bromide will come along and hit that carbon in the backside, knock off the water, and we go back to the starting material. So this is actually a process that's in equilibrium. We use Le Chatelier's principle to drive the equilibrium, meaning that if you want the reaction to go this direction, you just flood the system with water. And if you want the reaction to go this direction, then you actually have to remove the water while you're running the chemical reaction. So this is a reversible process. Now, the way you remove water, the simplest way, it doesn't work extraordinarily well, but it works well enough, is you just put the same drying beads they put in new shoes and beef jerky that soaks up extra moisture. We actually just put those, we don't bother to put a package around them because we assume people aren't going to eat them in the laboratory, but we just pour those little silica gel beads directly into our reaction flask, and it kind of scrubs the water at a molecular level that pulls the water out of the reaction container. And when you're done, you just put those little silica gel beads inside of a drying oven. You boil off the water and you're ready to reuse them. So it's something you can do in the lab. If you ever want to do like an at-home laboratory for whatever reason that you want to convert alcohols and alkyl halides, which I'm pretty sure does not involve, that's not how you make meth. So you can probably do it, nobody will care. Then you can actually use those silica gel beads as a way of pushing the reaction from the right-hand side to the left-hand side. This particular reaction is actually called a solvolysis reaction. Going from left to right, we call this solvolysis. Solvolysis, if we break that down, it involves solvent and lysis. Lysis means to break. So what it means is we are breaking apart this molecule using the solvent, and the water does tend to be the solvent. One of the laboratories that we typically run for first semester organic chemistry students involves the mixing of an alkyl halide directly with water and something else to mediate the solubility. And students run that solvolysis reaction. Solvolysis is a generic name, meaning that it's whenever you mix any solvent with something and the solvent breaks it. A more specific term for solvolysis depends on what the solvent is. This is actually technically called hydrolysis. So the mechanism going from left to right has a name, and it's called hydrolysis. More generically, it's just solvolysis with water. You can do solvolysis with either water or methanol, and that's what this next question is asking us to show, is the solvolysis of an alkyl halide using either water or methanol. What generally happens in a solvolysis reaction, now this right here was a primary alkyl halide, so we can't make a carbocation because it'd be primary, but if we have an alkyl halide and we soak it in water, you can also get an SN1 reaction to occur. I'm going to go ahead and help you later build another table that allows you to predict if it's SN1 or SN2. But if you want to start kind of diagramming that out, then you should know that the solvolysis reaction for a primary alkyl halide goes via SN2. That's what happened up here. For a secondary alkyl halide, it typically goes via SN1, which means that you're going to go through a carbocation. And what happens in the first step is the bromide actually gets it just falls off, is what we typically show in the mechanism. And in fact, in the mechanism itself, you don't technically need to draw out any of this water stuff. So I can actually just get rid of this, and this mechanistically is correct. The problem with showing the mechanism like this is while it is correct and definitely the way that chemists will do it, it doesn't actually explain why the bromide just fell off. Bromides aren't supposed to just fall off in the same way that our pets' heads don't just fall off. And so what actually is happening inside of the solution is the water is having, this is not a hydrogen bond because this is not an oxygen, nitrogen, or fluorine, but it's still a pretty strong interaction. And if you surround this with enough waters and they're using the partial positives of their hydrogens, they will kind of pull that bromide off. But since we don't like to show solvents in our mechanisms, it's bad form, then the best mechanism actually just shows it like this. And so the water is kind of there to help you understand why the bromide just up and leaves. It doesn't. It actually kind of gets teased off by the water molecules. And then one of those waters, it's kind of a group effort here, the waters will collectively rip the bromide off, and then another water will slide in its place, and you end up with an alcohol. Well, you have to deprotonate it. So there's 1, 2, 3 total steps. This is definitely an SN1 reaction because it involves the formation of a carbocation. And if you'll notice, if I had given you this as a secondary alcohol and had told you that HBr was present in solution, which it will be, you're going to have acidic conditions with the hydronium, you got bromide ions floating around, there's some HBr in there, you would tell me that that would go SN1 because a secondary alcohol reacts with HBr in SN1 fashion. The reverse reaction here, where we go from the alkyl halide back to the alcohol, also goes via SN1. SN1 is not something that we've talked about on this lesson until right now. Not really, anyway. And the stereochemistry of SN1 is shown here as a squiggly line. What a squiggly line means to a chemist is both things are happening. This compound I started off with was cis. Both the bromine and the methyl group are on the same face of the ring system. But when the water adds in, the water actually comes into either side. So what I've done down here on the bottom is show you this methyl cyclohexadienyl anion, or cation, I think is what they call that. But this carbon right here, and I don't know why I have an extra line right there. This carbon right here on this side is a sp2 hybridized carbocation. That carbon right there is sp2 hybridized, and there's an empty p orbital. And when the water comes and sticks to it, which is what that mechanistic arrow is showing right there, the water can come into either side of that p orbital. And so some of the time, the final product will have an oxygen that's on the same side as the methyl group, and some of the time, the oxygen will be on the opposite side of the methyl group. We'll learn later on how to predict which side is more likely, but for now, both of them are probable. And if the oxygen comes in on the opposite side of where the bromine originally was, then we call that stereochemical inversion. If instead the oxygen ends up on the same side where that bromine used to be, that's called stereochemical retention. So mechanistically, this reaction right here is called a Solvolysis reaction. I don't know why I just lost part of my slide. Let's try that again. Nope. Evidently, it's going to get cut off. So in this mechanism right here, it's an SN1 reaction. This is called a Solvolysis reaction, where the water essentially pulls off the bromide, and the water is a solvent, so we don't show it pulling off. We just kind of show the bromide leaving, and we assume that people know that it's actually the water that pulled it off. Water then captures the carbocation. Either water here or a bromide ion can act as a base to clean everything up, and you end up with your final alcohol product. Because it went through a carbocation, then it's going to sometimes the water will come in on the opposite side and we'll have that stereochemical inversion. And sometimes the water will come in on the same side that the bromide just left, and we end up with stereochemical retention. So going back to our definitions at the beginning, stereochemical retention right here is a possible result of an SN1 reaction because the carbocation intermediate is not chiral, and the new nucleophile can attack from either side. So it's not that in an SN1 reaction you only get stereochemical retention. You're also going to get some stereochemical inversion. It's just with an SN2 reaction, it's almost always inversion, and an SN1 reaction, there's some retention there as well. Sometimes the new atom stays on the same face where the old atom left. I suppose we have one definition left, and this is solvolysis. This is a nucleophilic substitution where the new nucleophile, or it's not new actually, it's the only nucleophile, is the solvent. And most of the solvolysis reactions we're going to look at are going to be hydrolysis. Most solvolysis reactions involve water and are called hydrolysis. And when I say most here, I mean most of the ones that we teach you in the course of a class. I'm sure that there's a lot of other solvolysis reactions that occur in a laboratory. And I haven't run a survey of all laboratories in the world to know which is the most common. On paper, it's usually water. What if it's not water? Well, that's this next question. What if we run the reaction in methanol? Well, methanol and water are actually pretty chemically similar. So I did the same mechanism. I just replaced one of the hydrogens on the water with a methyl group, and the same first step. So I start off with this same cis 1-bromo-4-methylcyclohexane. The bromide falls off in the first step. I have a little note here for my own edification that the hydrogen with a positive charge is kind of helping that bromine come off, but you don't want to necessarily show that in your mechanism. It's more of just kind of a little bling there. Once the bromide falls off, then the carbocation that's formed, this oxygen will throw its electrons at that carbocation. Either a bromide ion or another methanol solvent molecule will come and deprotonate this hydrogen, and we'll end up with a very similar looking product to what we had in the last case. And we also see that same stereochemical scrambling that occurs, where some of your final product will have a cis relationship because we retained the stereochemistry, and some of it will be trans because we inverted the stereochemistry. So solvolysis can involve any solvent molecule. Water is definitely the most common. Methanol is a distant second place, and I've never really had to deal with a third place. I guess ethanol would probably be the next most likely, and maybe after that ammonia. But after that, we really don't care too much. Typically water, sometimes methanol. This is solvolysis. Let's check to see if we've wrapped things up. We got all the definitions in place here. And now we have the required textbook problems, and then we have some chalkboard problems for you guys to work with. Of the textbook problem, 6.1 is a uniquely important textbook problem. And the reason for that is you're going to start to see a lot of different nucleophiles in this chapter. I already showed you a couple. We looked at methanol actually is a nucleophile because it captures the carbocation. Water is also a nucleophile right here. We have a bromide. Nope, that's not. Chloride, iodide are nucleophiles. Here's a thiolate, a sulfide nucleophile. So I've kind of thrown a bunch of new nucleophiles at you, and this question number 6.1 walks you through all of the nucleophiles that you need to know. So after you answer this question, you can compose your own list of new nucleophiles that you should memorize. And I tell students this every time, and then they never bother, and then they ask me to come up with that list for them, and I reference them back to this problem, and it's just a circular issue. So take a minute when you're answering this question to go ahead and, for your own sake, compile the list of nucleophiles that are all summarized for you in this question right here.